that opened up that's exemplified by the graph that's there. What you see in the graph is the x-axis is just time, years, the y-axis is performance. You see that the disk drive is relatively flat performance. Good job of increasing capacity, but performance is relatively flat. And the demands is because of CPUs getting higher performance, multi-core CPU, multi-threads, demanding more and more data. You have these large gaps in performance that have opened up. People try to solve that in a lot of different ways, a lot more DRAM in the system, a lot more power, various type of approaches, but basically this gap towards what von Neumann was looking for, the data is not close enough to the processor. So Rob's going to talk about how we start to solve that problem.
Yeah, we start, of course, in the 2008 timeframe with the ramp of bringing semiconductor memories into storage more aggressively with NAND-based solid-state drives. And here we plug a big chunk of the gap between hard disks and memory speeds from the storage side of the computer, and something that is 100 to 1,000 times faster than the hard disk, but with still access to that storage medium. And here we've sort of been able to unleash the microprocessor and the computing system from a big chunk of the I/O bottleneck to the point today where this is becoming much more the industry norm, to be inserting this new level in the storage memory hierarchy. Solid-state drives have gone from the modern beginning of solid-state drives penetrating computing in 2008 timeframe to today, where they're really turning to be mainstream in both client and cloud data center and data center markets. But the challenge has continued, and we see this continued explosion of data and the need to get access to that data and the value in accessing that data to turn it into information to solve very real problems. And that is about getting access to that data quickly in large amounts in a timely manner. So we can use complex large data analytics to solve fraud and predict fraud early, but only if we can predict it in a timely manner is that information valuable. If that takes too long, obviously it's not as useful. In financial services, it's about predictable transactions, low Q-depth activities. Online advertising is about quickly getting the most valuable ad that's useful, personalized to the shopper. Scientific research folks are making compromises in the resolution of their data in order to get scientific research done in the time frame. And in gaming, of course, I see Chris just stepping in here, it's about immersive, sustainable play in gaming, not interrupted. And we want a rich, immersive experience that we can continue to sustain without interruption. And so this explosion of data, it says that solid-state drives based on NAND technology coming from the storage side of things is not enough. And we've been working for quite some time on what comes after that and what comes in addition to NAND-based technology, and that is this new class of memory, 3D crosspoint technology. And we're pretty excited about that. We see it at the physics level and as well as at the attributes that that memory technology brings to you, making it a new class of memory beyond just a simple extension of something that's already existing. And we want to describe what's going on there a little bit to you, and tell you a little bit about what's happening inside the 3D crosspoint technology. And Al's going to talk to you about that.
So the 3D crosspoint, we're really trying to go after what von Neumann was talking about, how to get large capacity, how to get it at small granularity of word access, and how to get it quickly available. I think Rob has a wafer there that he's going to
oh yes, I'm show. Yeah, and we have them actually in Vanna White over here for Al. And so this is a 3D crosspoint wafer, and this has on it each die on this wafer is 128 gigabit die, and
there's probably about 5 terabytes worth of data on that wafer.
On a given wafer. So we're getting some pretty high density, and you can see that it's not a figment of our imagination. Those guys with the keynote earlier, you saw us demonstrate that, And this is, your view of what it looks like in wafer form as
Yeah,
well.
so since it's a little bit difficult to look into that, we brought a little bit of a model here. This is about a 5 million X blow up. So what you're seeing here is about 32 memory cells compared to each die on there being 128 gigabit memory cells. So we talk about a 3D crosspoint. What is this? A 3D crosspoint is really kind of named at the simplicity of this structure. It's a crosspoint because what it represents is the crossing of two lines. And so you have a word line and a bit line in the blue here. These are metal lines in the back-end processing of a silicon process. They cross. It's the smallest structure you can build because it's just a line and a space between them. It's 3D because it's stacked in 3D. And it's on top of the underlying CMOS that would be down over here. That would be the normal CMOS that would be controlling, the word line voltages, bit line voltages, sample amplifiers, things that you need to do the normal memory operations. They get folded underneath the memory array. And so how is it that we get towards this, closer towards getting more of this data closer to the processor? Well, the first thing is by getting it to be storage, which is non-volatility. In the case of this technology, unlike NAND or DRAM or SRAM, which all use charge, it's all electron storage on some node. In the case of NAND, it's on a floating gate. In the case of DRAM, it's a capacitor. In the case of an SRAM, it's an internal storage node. It's all charge that's being stored. In this case, we're using the atoms of a cell, of the memory cell. It's a bulk property, so it's all the atoms. So instead of just having a handful, it's all the atoms, so you're dealing with hundreds of thousands, millions of atoms in a cell like this. And because it's atoms, once they're in a bonding state, there's a higher energy barrier, so it's inherently non-volatile. When you take the power off, that the bonding state of those atoms is not going to be destroyed. So it will be non-volatile, meaning you unpower it, it will remain the ones and zeros. What's really critical here, you see kind of two colors here, a yellow and a green, and that represents kind of both the memory and what we call a selector. Since this memory is a resistive change element, you have high and low resistance being the ones and zeros. If you had a cross point and all you had here was a resistor, you would end up with all these resistors having crosstalk between them. It'd be like a giant Kirchhoff's equation that you'd have to go solve. And so what you have to have is a selector. Think about it as a thin film diode that isolates one resistor away from another resistor. And what's critical here is how to have a selector material and a memory material that are compatible with each other. So they're compatible process-wise, they're compatible chemically, they're compatible electronically, and get these to be mated up to each other. So that's what achieves the non-volatility, what you see in the upper right. The fact that these are fast switching materials, if we go down to the lower right, these are fast switching materials, and this is all in the back end metallization, so it's low resistance interconnects that are in here. You have very fast access. This has access up to 1,000 times faster than is in NAND, and that's both for read and for write. Going to the lower left, since this is a cross-point type of architecture, and it's in 3D, this is very highly scalable. We can scale up into putting more decks in here, and then also you can scale lithographically. Think about just shrinking the volume of this as we shrink the lithography, going to smaller and smaller dimensions. Moore's law is basically we don't go down to smaller dimensions. The wafer that Rob showed you there is a 20 nanometer technology. So it's very high capacity. The fact that, again, this is a cross point going to the upper left, you select one word line, one bit line at a time, so one cell gets access within a tile. This gives you fundamentally low granularity, and so you're able to achieve word level type access, which is kind of the access that you want down in kind of cache line sizes for the processor.
So when we look at implementing this technology from a storage perspective, actually, you want to talk about storage and memory?
So Rob likes to steal my slides. So go back to the kind of slide we showed before. Let's go put 3D cross-point into that. And you see now we've taken two worlds and we put them together. Storage, memory converged. Think about all of them together. You see now it has latencies, not as fast as the fastest DRAM that's available there, but it's 1,000 times faster than you have in the case of a storage technology like NAND. And it has capacity similar to what you have in NAND. So Rob is going to talk about now what is it that we can see when we take 3D XPoint, we put it onto a standard storage bus.
Yeah, so as you know, we've been working on putting semiconductor memories into storage for quite some time. And originally, when we have low penetration into that market, we have to fit into the hole in the box that exists already, into the buses that exist in the PC platform already. And that is the SAS and SATA interfaces. And those are great interfaces for rotating media. And because they're efficient, and compared to the media access time, which is not drawn to scale here on the left, if it was drawn to scale, it would be going through the roof of the building. They're very small. But when we moved to semiconductor memories, we could take advantage of them. They were useful interfaces to us, but they are somewhat limiting in terms of latency. And so you can see the ratio of the blue to the yellow, if you will, gets to be much larger. So we've been working on a new standard, NVMe over PCIe, in order to streamline that process, to get the interfaces to the platform to be much, much shorter. And we were doing that because it's important and valuable for NAND-based technology, but we were also doing that because we knew 3D XPoint was coming, and we knew that we needed to drive a new normal, just like we have with SATA and SAS for NAND. We need a new normal baseline to start with for 3D XPoint. And you can see that if we were still on the old interfaces, the media interface would be a huge problem. And in fact, it's still somewhat limiting, but it is a huge improvement from what we would be doing. So these technologies, 3D XPoint technologies, will all be driven on NVMe over PCIe. And the first set of products that we develop from the storage side of things will be the new Intel Optane technology products. And this is the combination of this 3D XPoint technology together with optimized memory controllers for those products, together with optimized interface to the platform and software that make it a complete storage product. And in 2016, we'll be bringing new Optane-based solid-state drives to the market to enable use of this technology across a broad spectrum of platforms, from the data center down to ultrabooks. And we expect the work that people do on top of this to be significant improvement in capability for the platform from data center down to gaming. And with gaming, we're pretty excited about that. Enabling truly immersive gaming with open world scenarios that have large data sets available to them that they can sustain uninterrupted play with and have a rich immersive experience that is fundamentally different enabled by the platform. But we're not going to stop with storage. In fact, there's more to it than that.
Okay. So as Rob said, we can put this onto the Intel Optane technology, which is with the 3D XPoint media technology, onto a standard storage bus and achieve, as you saw if you went to BK's keynote this morning, kind of a 5 to 7x performance improvement. So you ask, well, wait a minute, didn't you say this is 1,000 times faster? Why is it only 5 to 7x improvement? And that's just basically kind of an Andol's law, right? You're limited by what is the next limiter in there. So how do we unleash the technology? The way we unleash the technology is taking it off of a storage bus, taking it away from having to do any sort of context switching, taking it away from drivers and putting it directly onto a much faster bus. Let's go put it onto a memory bus and let it have access to the processor. Let's unleash its speed. Let's see that in the next slide. And so we plan to bring to market DDR4 electrically and physically compatible DIMMs based on 3D XPoint technology in next generation Intel Xeon platforms. This is going to offer up to 4x system memory capacity increase over standard DRAM at a significantly lower cost. And also, it can plug directly in with no changes whatsoever to the OS or to the applications, and you have the benefits of big memory systems. Now, that's a lot like what Rob was saying, is that, hey, we can go plug things in directly in an SSD and things will work in there. And then there's opportunity with software changes, as Chris was talking about in the gaming mega session, that if you optimize now around that, you can do things, because people have been writing all this software, doing everything with bottlenecks in mind. As soon as you unleash those bottlenecks, then we can really take advantage of it. Similarly, when we put this onto a memory bus, it can operate directly without any changes to the OS in our applications. But obviously, those applications and OS have been written with bottlenecks in mind. And as you optimize that software, then you can really unleash the potential that's in there. And if you want to hear more about that, at tomorrow's big data session, big data and IoT session with Diane and Doug, they'll be talking more details and kind of what's behind the scenes.
Yeah, should be exciting. And so, although it doesn't require, the technology doesn't require software rewrites, there's certainly the opportunity for that. The technology is very exciting for us. We've been working with some of the leaders in the industry about how they would take advantage of the technology. We've been thinking about that. I wanted to show you a short video that gives you some thoughts about how people might use the technology.
Our digital lives generate unimaginable quantities of data. 40 zettabytes by 2020. Children born today expect the power of computing to be fully realized. That they will have instant access to that data anytime, anywhere. Information, services, and experiences need to be available with a click. They don't care about cache line size, random data access, and queue depth bottlenecks. Every online transaction needs to be seamless. She expects a shopping experience free of fraud or security concerns, while advertisers want to reach exactly the right consumer at exactly the right time. Faster and affordable access to huge data sets will keep them both happy. He expects his doctor to understand him at a genetic level. Computational genomics needs faster access to data to improve accuracy and enable doctors to catch problems sooner, treat illness faster, and one day provide the cure he'll need. The immersive, open-world, uninterrupted gameplay he expects has been unachievable with current memory solutions. Cinematics, load screens, and level changers are band-aids designed to mask the memory bottleneck. A whole new generation of users demands more. Intel has responded with 3D cross-point technology. And as developers, it's our job to deliver. What will you do?
So we are excited about some of the technologies and applications that folks we've been working with in advance, the big data analytics that will help companies run more smoothly, countries run more smoothly, the immersive gaming applications that will emerge. But we are even more excited about what we haven't thought of, what people will do, what people will invent on top of this technology. And with that, I'd like to open up the floor. If you have some questions for Al and myself, we'd love to answer them. There is some microphones.
All right, you can stand up and ask your question. All right, great achievement. Questions, how many decks can you do economically? Can you do multi-bit per cell in the technology? And is data retention measured in years, months, or days?
Number of decks, MLC, retention, was there a fourth one in there? It's three. Okay.
Let's start with 3.
I could ask you about bit error rate, but I
Okay,
won't.
3 questions, 1 beer, Dave. Okay. So, number of decks, the first generation is 2 decks that we're going to production with. In the future, we are going to multiple decks that are in there. This is a different technology than is used in 3D NAND, where there are multiple layers of a very large size structure, and then with kind of one etch that goes through. And so this one requires multiple layers of lithography as you put more decks on. Probably the economical number is going to be somewhere in the 4 to 8. Beyond that, when you start adding, you double up the cost as you double the number of bits. And so you get higher capacity, but you're not lowering the bit cost per bit because you've already amortized the underneath CMOS. So it's in about the 4 to 8 decks.
And then Al will be back in 3 years and tell you how he's doing 16 decks. I suspect.
It's usually what we can see at any given time. This also can shrink lithographically, so to smaller dimensions, following a Moore's law type of approach. It's a very litho-friendly in terms of its scalability. In terms of MLC, yes, it is capable of MLC. I can show you an MLC graph if I wanted to, but I also think it's a waste of time because that's a lab presentation. I was lucky enough to work on the first generation MLC flash in the industry. It took us 10 years from the first generation of single level cell flash to the introduction of MLC. And when NAND came out, it was also about 10 years. And the reason for that, it's not what you do in the lab as a proof of concept. MLC is all about manufacturing margins. You have to understand all the sources of variability of manufacturing. And so as we get this through manufacturing, understand all those sources of variability, understand how we can tighten that down, understand the usages, we'll be deploying MLC on our roadmap. And your last question in terms of retention, the retention is measured in years. This is a non-volatile memory. We measure ourselves against a standard very similar to how storage would be done today in the case of NAND SSDs. And so when we look at SSDs, we look at DIMMs and think about them as non-volatile memories. We think of them as along the same lines very similarly as a NAND storage, which is years of data retention.
Awesome. We got one over here.
Yes, are there high and low temperature thermal storage limitations?
As in any semiconductor technology, there are high and low limits on that. I'm not going to release the specs at this time of products. We're not talking about products, but products will follow normal thermal limits, and you'll see that on product specs for various products.
So we aren't talking technology today. We are talking, we're going to do some products, but if you want to know the exact price and availability of that product, that sort of thing, we're not ready to do that, or the exact specs and SKUs. We'll do those, as time, when at the appropriate time for releasing the product.
I'm Jerry Harris, Principal Scientist in Photoshop, and I posted this to Internal Compete Forum when you guys revealed it a couple of weeks ago, and every single editing app was like, oh my goodness, this changes everything.
Yeah.
Because we spent our whole life waiting on disks. It doesn't, the only thing that's really improved, high-end $5,000 workstations has been GPUs getting a little better, but this will make a big difference. We'd like to get it, any way possible, we'd like to make sure we don't have such bottlenecks, and when you ship this, it gets in the way of impeding performance.
Yep, we're really excited. Actually, I think there might be a demo down in the showcase of one of your products where we're doing 4K video editing. That is, a great example of using NAND flash memory, but this, with that kind of multiple stream editing is really benefit from this random high.
Photoshop's even worse. There's 1,000 layer files that are
very cool. Yep.
Alan Evil, is the rate latency deterministic?
Yes.
Okay.
We're treating this as a memory, so reads and writes are deterministic.
Does the write current scale with the lithography?
I'm sorry, can you say that again?
The write current, does it scale with the lithography?
I'm not going to go into details about that, but we have a scalability path that we're very confident in.
Hi, Ian from Nantec. I've got two completely unrelated questions. Can you use one of the bit lines as a word line for your multi-deck designs? Multi-layer designs?
This is the middle cross-point wire.
So if you wanted to, you could do an odd number of layers?
Yes,
Okay.
yes.
Second question is...
The granularity is a layer at a time.
Starting with
This is
one
just-
being an odd number.
Sure, yeah.
as an example.
And when it comes to gaming, you're saying you're really interested in bringing this to gaming. Are you specifically talking just about the server side of gaming, or do you eventually want to see it in the end user, in-home sort of gaming?
Yeah, no, I personally, and I'm, let Al answer as well, but the enthusiast market for gaming, on the client PC will benefit tremendously from low latency, fast storage, and so, yeah, absolutely.
But you've only set it on the Xeon platforms, not on the consumer.
Well, so on the, just wicked fast storage, if you will, is going to get rid of those load times, right? It's going to enable us to take small bites, and continually feed them into the game.
So sorry, I'm speaking specifically about the memory here, not the storage.
About memory, yeah, the technology is equally applicable into that market. Today we were talking about Xeon-based platform.
Gil Russell.
And the factories, if you're looking at
I guess it's two questions, actually. One, solder reflow, the old phase change memory. Can you put it through phase change? Can you put it through the solder reflow? It has to be, in other words, what's the upper limit of the temperature limit, and does that degrade the durability of the memory?
So I'm not going to be speaking about what the technology, the underlying material science or physics of it. But what I will say is that what you saw demonstrated today in a prototype SSD is, wafers that are diced up, assembled, put onto a board through solder reflow, and things are working. And so we know how to manufacture it.
it's never going to be enough.
Go ahead and stand up and ask your question.
I wondered if the durability is up there to be able to, basically you're saying, run alongside DRAM as a scalable memory type. That's what you're aiming at next year, you were saying, I think?
Yeah, that's right. That's the plan.
The durability is really the same as the...
Yeah, we're saying it's 100,000, times that of, 1,000 times that of NAND.
Okay, thanks.
Yeah, can we assume that we're going to see this as a memory solution quite a bit before we see it as a storage solution based on 3D NAND is getting really, really cheap, and it takes volume to get the costs down on new technology like this. So does that mean that this is going to be a memory solution first, and then when would you expect it to be a storage solution?
Yeah, what we said was that we were going to deliver storage in multiple form factors in 2016, as well as deliver memory DIMM for the new Xeon platform in 2016. And so that's the timing, if you will. What we, I think your premise that it's not great in storage, I think might, I would argue with you about that a little bit. I think it's awesome storage. The fact that it's 5 to 7x the performance of the existing technologies. There are a lot of, with very high quality of service, predictable, low latency for transaction-based platforms in the data center, or for the type of the enthusiast and media applications that we were talking about earlier. It's going to be awesome for the desktop platforms as well, client platforms as well.
Hi, I know you mentioned that it's, we're back here. It's a DDR4 electrically and mechanically compatible, but is it fully a JEDEC standard, or are you going to go for a release of the JEDEC version?
So this, it is electrically and physically compatible with the DDR4. It does require the new platform because this is a new, this memory technology is a new technology, and the platform needs to understand that.
cross-print in the same sort.
Yeah, just referring to DDR4 interface again. Is the actual technology thoroughly random access? So could an SRAM implementation be done as well, or will you just stick with the routing CAS approach?
It's a random access technology.
It's a random access technology, it's probably 1 million times denser than an SRAM, I think if that's what you're asking. Is that what you're, yeah. A lot denser than an SRAM and non-volatile.
So are the read and the write latencies symmetric or asymmetric?
We're not going too much into the device specific characteristics. I will say both read and write are 1000x faster than in NAND, and so and you saw that the result of that through the SSD demo this morning.
That gentleman over there against the wall has had his hand up. Let's give him.
Hi, given that this is produced in the IMFT venture with Micron, are there any restrictions on you selling this in a component form? Are there any restrictions on Micron selling this to your processor competitors?
Yeah, so we believe that this is an exciting new technology and that it's new and disruptive, and the best way to bring this to market for us is through a module form factor, both either DIMMs or solid-state drives. And you can see that in the way we brought our NAND memory technologies to market as well. We don't sell many NAND chips anymore. It's all driven through modules focused on high-performance computing, right? So we're not participating in the markets that are not, as you would expect, adjacent to Intel's core business. So we're going to be driving solutions into the marketplace that work really well with Intel's platform solutions. And then, for Micron, that's Micron.
Great job solving the memory bottleneck. Can you speak as to how this will enable new CPU architectures to leverage what you have here?
Well, I'm not a CPU architect, so if there is a CPU architect in the audience, I apologize in advance for my answer. But I think you'll see that actually in this next generation Intel Xeon processor. It basically is something that is re-architected to recognize this technology, and so that's the beginning of that. And I'm sure that there's a lot of bright minds out there that are real smart in computer science, better than I am, to figure out where that goes.
Yeah, I would just add that this is an opportunity to realign the computer memory storage hierarchy, and I think this will take us a little bit while to resell into that, but there's certainly opportunities for that. And the other is that it's removing the I/O bottleneck. So a lot of things that were I/O constrained then become CPU constrained, and so that gives us more freedom to deliver higher performance capability in the CPU that applications can take advantage of because we've moved one of the bottlenecks out of the way.
Back to a question on the memory channel use case. It says 1000x more endurant than NAND for writes.
Yep.
But DRAM is still 1,000,000x past that. So how do you close that gap? How do you cover that gap?
Yeah, so at a basic technology level, think about NAND itself. NAND has, probably 1,000 cycle capability, yet you're using it inside of an SSD for multiple years. How is that occurring? Aren't I writing that same file over again? Is it my security, that I'm using, my McAfee security, rewriting the same address all the time? There are things that you can do to kind of deal with that, and so
there's I think it's simple. There's simple things to do to manage that.
Yeah. I'm just saying, though, there are simple things you can do to manage a media inside of a memory semantic.
Do I expect more power use than the NAND technology, or it's a power use for the same scenario? For example, like video playback with the same content. Is it this cross point is using more power than NAND, or it's a similar?
It's a lower power.
Lower power then?
So you mentioned you were planning to release this as DIMMs and SSDs. Do you have any plans to bring it to the embedded space at some point?
Yeah, actually, I think that when we go to the embedded space, you think of it as for SSDs, PCIe, the small form factor M.2 PCIe products are a great solution for that. 22 millimeter by 30 millimeter, let's just say, fairly thin products. And then long term, we can deliver more optimized products. Think BGA form factor or something like that.
For your next generation processor that we're not talking about, if I were to use this crosspoint and mix it with normal DRAM, is it going to impact my bandwidth or performance of the DRAM? Like interleaving, is that going to mess things up?
My understanding is it should not impact that. You can talk to Diane or one of the folks after the fact. It's probably a little too early to be announcing the details of that.
Earlier today, you were showing performance versus the P3700 of about 5 to 7x. I assume that's effectively hitting your PCI Express bottleneck at that point, right?
There's probably more we can do there, but getting the difference between that and getting to much higher.
So we effectively have to scale beyond our current PCI Express in order to get even more performance, right?
Yeah, there are things we can do around if you want just more IOPS as opposed to latency, to get wider interfaces to that we can, and then obviously PCIe is evolving over time as well.
So one of the things that you mentioned earlier was you had the control circuitry below the actual stack. Are there restrictions to putting other things like processors under this in terms of thermal or other process related?
From a theoretical perspective, the answer is no. We utilize all the spacing here kind of very efficiently for doing all the read-write circuitry, all the sense amplifiers, and things like that. In theory, you can kind of put a processor on there, but in general, what you want on a processor versus this technology tends to go in different technological directions. Microprocessors are, many multi-layers of metal, highest performance, lowest voltage transistors, and it's trying to extract every ounce of performance out of it. In a memory technology, this is wonderful about having the high performance capability, but at the end of the day, low cost is still a driver of memory technologies. And so, putting it onto, something that has, 8, 9 layers of metal is adding a lot of cost versus what you want to do for optimized memory.
Quick question, will this cannibalize the NAND market, the DRAM market, the CPU market, or is it a system cost saver?
We haven't launched a product yet. The way I would look at it, Gus, is that it's a new level in the memory hierarchy. And yes, it could impact, one or the other of those, but I think it's a little early to be making predictions about that. For now, we see it as solving a compute problem, and, the applications that it solves some of those compute problems in will be inserting a new layer in the hierarchy more than likely.
Joe Russell. There's been the GHOST program that's been galloping around and hard to see. That's part of Intel. It's called Crystal Ridge. And as I'm finding out, Crystal Ridge has to do with persistent memory. And if you will, it's the never off condition of a durable state system. I was wondering if you could give me a little color on how this dovetails into the
We don't see ghosts.
We don't see ghosts.
As the short answer.
Is this technology a type of RAM, resistive RAM?
You might think of it in a broad class as a resistive RAM. It's a material system that changes resistance, high and low resistance, as the ones and zeros. Probably the distinguishing feature is that when most people think about a resistive RAM, they think about a film entry approach. And in filamentary approach, where you're dealing with the difference between a 1 and a 0 can be as often as few as 10 atoms. And so you have a lot of stochastic variability in there. This uses a bulk property of the materials, and so now you're dealing with all the atoms. You're dealing with hundreds of thousands of atoms, and so now the variability is not deal with in processing. What's the thickness of the films? What's the critical dimensions? And those are the things that we understand how to deal with very well in semiconductor manufacturing.
Probably going to figure out I'm asking the same question again. Are there possibilities or plans for industrial or automotive grade products?
At this point, we're not announcing any products. We're talking about the technology.
But the short answer is I think there's broad applicability to the technology, over time. So we would love to talk to you more about that. Can't be done. Yeah. Okay.
I think you mentioned earlier that initially this would be a 20 nanometer litho step. Just kind of curious, what kind of cadence should we think about from scaling, and what kind of density improvements? Is this going to be a 2-year cadence, and what kind of density improvements would we expect over time?
No, I think you can have something in mind that's sort of similar to what you see in NAND type of technologies, which is, every year and a half, couple of years, as in NAND, you see kind of doubling of densities. This should be kind of a similar type of thing. It follows a Moore's law type of approach with scaling.
Hi, Jim Handy over here in the corner. I have been puzzled by the way that the thing looks with the select devices and the actual bit cell and word lines and bit lines. What I'm more used to in something stacked up is that the select devices would both be touching word line, is it, or is the bit line? I forget which. And the bits, so in other words, you should have yellow and green on one and then have it flipped over on the other one. Is there something inaccurate about that model, or do you actually have them all pointing in the same direction?
Other than the colors are not actually the colors that's on the material, and the size is 5 million times larger, it's fairly representative.
Other than those small discrepancies.
But my wife tells me I can't distinguish any colors either. So.
Me too.
Hi, I'm Mark Reberg. Question, what kind of ECC do you expect that people will use with this technology?
As Rob talked earlier, we're not, delivering we don't anticipate delivering these as components. We're delivering these as solutions, whether it's a SSD solution or a DIMM solution, and so that's an internally managed.
So for the DDR4, the cross-point DIMM, so your slide shows that it acts as the write cashback. So that is the only mode is you can utilize with that DDR4 cross-point DIMM or not?
That's what's being disclosed right now, as that on that slide. You can go to Diane's mega session tomorrow, see what she has to say, and then over time as we get closer to product, see what those details work out to be.
Hi, we've heard of 3D crosspoint technology in two interfaces today, the NVMe and DDR4. Is it going to be limited to those, or will it be deployed in other channels as well?
Yeah, we're excited about the future, right, beyond what it is we're doing here today, right? We talked about a few things, right, but we believe the technology is broadly applicable, and, we're excited about what we invent together, about solutions to solve computing problems for the long term. So, whether we get to 16 layers or 8 or whatever, the future is still unwritten, if you will. I think we can probably take one more question, and then we're going to be out of time.
Hi, this is Eli Stern. I was wondering if you could talk about the native interface to the 3D crosspoint devices themselves, particularly in context of the DIMM solution. Is it something that native goes on native to the device interface?
Yeah, no, we're not talking about that next level of detail. The way we're looking at interfacing to this is at the module level, and I think that's important for the early type of technology that we're talking about here for the first generation. We're going to do a lot of work here, right? And we're going to run very fast, and we want to have the freedom and flexibility to be able to do that.
One more question, guys. One more.
Looks like that's it.
Okay, hey, thanks a lot. We're excited.